Okay, let's start. So this is the last class of this term for this course. And today I'm going to talk about the so-called, in a bigger theme called stochastic optimal transport. So we try to consider optimal transport where there is some constraint given by probability. But of course, you learned the Schrödinger bridge problem, which is about Brownian motion. So you already saw some direction in stochastic optimal transport. But the thing we are going to consider today is another direction. By the way, can you hear me well in the Zoom? I cannot hear you, sorry. So can you say something?
Yes, we can hear you.
Oh, okay, good. Thank you. All right, so basically, I'd like to talk about these two things. One is optimal martingale transport. The other one is optimal Brownian stopping, and its application to free boundaries. Okay, here are some main references. So for optimal martingale transport, okay, there are some other previous works, but I really like this work by Biggebach and Juliet. They are probably the first people to consider kind of the structural question of this optimal martingale transport problem. And then, of course, I also worked on that direction, and then we were able to, with Nasif Gus and Dong Song Lim, my former students, jointly with Nasif, we were able to kind of extend their result to general dimensions. So their result was for 1D, and then we did it for more general dimensions. And there is another direction related to the optimal martingale transport is optimal Brownian stopping. So here again, Biggebach was a pioneer, and so with these two other people, Alexander Cox and Martin Huesman, he kind of they realized that the famous problem in probability called the scalar embedding can be realized as an optimal transport problem, okay, with some probabilistic constraint. Okay. And there are many related work in this direction. And also I, with Nasif Gus and our former postdoc, Aaron Palmer, made some progress in that direction too. So these are like two papers. Some of the two of the papers we wrote, and later the ideas here was considered in particular in relation to the so-called the Stepan problem, a free boundary problem of the heat equation. And we kind of work with Inwon Kim and UCLA, we were able to formulate the Stepan problem as a free target problem of this Brownian martingale transport problem, which later was to extend it to, among other things, this non-local case. And then more recently, last year, Sonny Che, Inwon Kim, and I myself proved some existence results for the so-called supercode Stepan problem in general dimensions using these techniques developed there. Okay, so that's kind of a explanation of these references. Okay, let me start with optimal martingale transport. So here, so one needs to understand this condition, martingale. So martingale means just in probabilistic terms, expected value of your random variable starting from initial point is the same as the initial point. So that is what martingale is. So in analysis terms or in measure series terms, it is this. So this let's say this whatever the random variable has distribution. So starting at x, it has distribution pi x. Then this pi x, if you integrate this pi x, then its barycenter, or center of mass, is nothing but that location it started with. So from the point of view of optimal transport, you can consider a transport plan between two measures, okay? Between two measures mu and nu. And this martingale condition means if you for this pi transport plan, you can disintegrate that pi with respect to this x variable, okay? Then that disintegration, okay? Each of such disintegration for each x satisfy this this condition that is center of mass in the sense of in Rn is the same as this point. So that means you have this diagonal y equals x, then those distributions given by the disintegration are centered at these diagonal points. Okay, that's the martingale condition. Okay, and then optimal martingale transport problem is nothing but optimal transport. You want to minimize this, where pi is not only a transport plan but a martingale transport plan, satisfying this martingale condition. So we have more restriction on the more constraint on pi on the transport plan. Okay, for this problem, sometimes they consider maximization problem too. I mean, but max and min are nothing but the changing the sign of this cost. Okay, so but for given cost, somehow they are interested in both maximization and minimization. Okay. Okay, and one very important comment is this. This is very famous theorem called Strassens theorem, proven like, I don't know, maybe 80 years ago now. I don't know, 60 years. 60 years. Yeah, 60 years ago now. Is that given mu and nu, to have any martingale transport plan, they have to satisfy certain condition called convex order. Okay, let me explain this. So let's say if mu is like Dirac at x, and nu is another Dirac at y, and obviously there is a transport plan between them. You just moved x to y, right? But here, for this mu and nu, there is no martingale transport plan. You can easily see the reason, right? Because martingale basically has to split the mass, okay? So from x here, the martingale transfer, whatever the target measure, should have the center of mass at x, okay? So if you move this mass only to this point y, then you cannot have this x as your center of mass. So martingale condition is violated. So martingale condition, although it's just moving, just translating the measure, okay, in particular, but the point is that it has to, it just transport mass only by splitting the mass and then spread over the region while keeping the center of mass. Okay. And Strassens theorem says, that splitting and keeping the center of mass actually is equivalent to this so-called convex order. Namely, for any convex function, the source measure and target measure has to have this order. This integral with the source measure is smaller than or equal to the integral with the target measure. So here, this condition, if psi is linear, then of course you can apply psi and minus psi, both are convex, then you can see that in this case, this is the same. In general, when you ask this for any convex functions, okay, then that is a convex order. And then to have, this is necessary condition to have any martingale condition, because, for example, you can apply, so just this is necessary condition. But then Strassen proved that this is again also a sufficient condition to have a martingale transfer plane. Okay, any questions so far?
Are we assuming that the first marginals are the same so that you get equality for linear functionals? Like, sorry, the first moments of mu and nu are the same?
So the first moment should be the same, right? Because of the martingale condition. So good point. Because that x goes to x is a linear function. So for the linear function there, we have equality here. So really necessary condition is that both measures should have the same center of mass as a measure in Rn. Okay, good point. Other question?
Thank you.
Yeah, let me move on. I think I already mentioned about this convex order. So this exercise says for these two measures to be in convex order, then the support of mu, like mu is like this measure. Then, so if nu was like this measure, then obviously there's no like a splitting of mu realizing this target measure, right? So in this configuration, there's no martingale transfer plane. So then mu has to spread out. So that means whatever the target measure that is realized by a martingale transfer plane is some kind of mass distribution around mu, okay? Right? And it's also possible to have like some kind of Diracs like this around this mu as the target measure, okay? Depending on the distribution, then, but the absolutely necessary condition is that this target measure, if you consider the convex hull of this, if you consider the convex hull of this target measure like this, then this source measure should belong to this convex hull of the target measure. It cannot go outside. Okay, because then there's no way to realize this portion by your target measure. Okay. If any mass is here, then there is no way to realize this as to split this mass, keeping the center of mass to these things. And then in the reverse order, if your x is here and then corresponding, if your x is here, then the corresponding target points, in this case, all these things, should have this as its convex combination. Okay. So just to be clear, example, for new goes summation lambda I delta xi below there is no martingale transport from mu to, okay? Question? So martingale transport has somewhat strong restriction. Okay. Okay, let me move on. Okay, in probability, they simply say martingale condition is this. Okay, so expected value of your random variable starting from initial x is x. So then the martingale transport said you want to you have two random variables with distribution of mu and nu, and you want to find a joint probability distribution, or joint distribution between x and y. Sorry, joint. James, what is the correct word for this? Given x and y. No, coupling. So you want to find the coupling between x and y in such a way that the expected value of y given x is the same as x. So this is a martingale condition. Of course, this is conditional expectation, right? All right. And then you can just rewrite the martingale optimal transfer problem as this. So this expected value part is nothing but integral of c d pi. Okay. And then this is just martingale condition. This is the marginal condition. Okay. So when you read a paper, don't be surprised by just seeing this expression. They are the same thing. Okay. Then, I mean, either way, one can consider this optimal martingale transfer problem. And somehow the problem was motivated by finance. So what does this maximum and minimum means? So martingales are kind of some of the fundamental mathematical model for so financial for asset prices. Let's say you have, let's say at time zero or today you have some distributional price of stock, maybe of one stock, and then let's say in tomorrow, you suppose you may not know the actual price value, but suppose you may estimate the distribution of the values. Okay. Then this joint probability, this coupling between x and y is what happens if the current price is like x. Then what happens tomorrow with the price? What should the corresponding price y? So given x, you have the corresponding y. So that's like a coupling. And then you will have many such couplings, but the assumption for the underlying assumption underlying about the coupling is that the coupling has to be martingale. Okay, because if your stock price is like, if it is a real line at x, then we don't have any like, and we can assume that it can go up or go down, right? Stock price tomorrow. I mean, right? You cannot just assume that it will go up always, right? And then we have probably total ignorance about what will happen. That means it goes up some amount and it goes down some by some amount, kind of with an equal chance. So that's martingale condition. I mean, we don't have any prediction about what will happen. So that's martingale condition. So the coupling should be martingale. So then among all these, we want to consider this expected value. It means this. if you are a financial company and selling an option, let's say if the stock price is like X today, and if the stock price becomes Y tomorrow, then I will pay you some value, right? That is what C is. Then you want to kind of estimate what should be how much amount you have to prepare to pay the customer, and what should be the minimum amount you can you still need to pay. I mean, what should be the maximum payment or the minimum payment? That is what these maximum minimums are. So this formulation kind of is related to modeling option pricing. Okay. Okay, and then because of this importance, there are many people still working on but had worked on this problem, and these are like important people in mass finance: Hobson and Dolinsky, all this, Schachenmeyer. Yeah, these are very Tusi, Sono. These are all important people in mass finance. Okay. Question? James, do you have any question? No? Do you have option? Did you buy any option? No?
I'm not think good enough to understand the finance market at this instant.
Right. Yeah. Yeah. Money is always difficult to understand. Price may not be martingales. Yeah. So the underlying assumption could be wrong, right? But this is kind of a simplified model, right? Yeah. Yeah. Understanding money is, I think, really difficult. So that's why there's a whole big industry trying to do something on that. Okay. Remark? Okay, then you may wonder, okay, what kind of cost one may consider? Okay, many cost functions, right? But of course, we are focusing on some simplest case, simplest but still very meaningful cases. Okay, then probably the first non-trivial cost you may think of is just a quadratic cost, like in Brennan's theorem. C is, let's say, x minus y squared. So in this case, what happens? So there is kind of surprising to me, but it's still kind of trivial that if C was just x minus y squared, then this martingale transport problem is not at all interesting. I mean, as an optimization problem. Why? Suppose what x minus c is c, then what happens to this cost function under the martingale condition? Okay, that is what is in here. So any martingale transport is an optimal transport. So this quadratic cost is not so interesting in the martingale transport problem. So the reason is this: you just break up this square, then you have this cross term. Then you can ignore this in the optimization because they are nothing but the given second moment of the mu and nu. But this one, if you look at this, you first integrate let's say this with y variable, right? For given x, then this one, integral y d pi xy, this becomes what? This becomes so pi
X.
is not just x. Yeah, so I was tempted to say x, but it's not exactly x, because pi xy, if you consider this integration, namely pi is like some measure like here on the product space, then x is here, then this integration is just look at this slice, but that slice is pi x, but it is with respect to in this case, if pi for pi in with this first it is marginal mu, so you have this condition, okay? I mean this is a disintegration, so you have this actually here you have d mu x, okay? So then after this, then you integrate it again with respect to x, then you get x squared d mu x. Okay, and this is just given value because mu is given, so its second moment is given. So this expression, which is just this cost, is independent of your transport. If the transport is martingale. So I made a mistake here, sorry. d mu. Okay.
We don't know the uniqueness of uniqueness of martingale transport, right?
Yeah, given mu and nu, there can be possibly many different martingale transport. Okay. Okay. So if mu and nu are in convex order, then by Strassen's theorem, there's a martingale transport, right? From mu to nu. So martingale transport is not so symmetrical because one has to split to get the other. So if the other one again split, it cannot go back. Okay. So martingale transport has some kind of a kind of direction. So it has some order. You cannot make this condition kind of symmetric. Okay. Or maybe that's good point to mention. Okay, so you exercise. Maybe I should have put it here. If mu is convex order with respect to nu, and nu is convex, mu and nu is in convex order in this way, then in fact mu is equal to nu. Okay, so do this exercise. Okay, but anyways, so when you have such a convex order condition, then you can find a martingale transport plan by Strassen's theorem. Then among them, you can consider the optimal one. And the existence of such optimal martingale plan is again, you can just apply the Weierstrass compactness of these priority measures. Okay. So existence is fine. It's not so, I mean, it's important, fundamentally important, but it's not so difficult to obtain. But more difficult ones are understanding, a more difficult question and probably more interesting question is to understand the structure of such martingale transport plans, because martingale transport plan make this splitting, and then maybe one may ask, what is the kind of rule for such splitting? Okay, because there can be many ways to split the mass. So is there any like a special way of the splitting for the optimal one? In other words, what should be the corresponding Brennan's theorem for the martingale transport? Okay, good. So that is the question one may be interested in. So given X, for the martingale transport plan, the support of pi or concentration set of the pi can be some set in the product space, and then like who knows, like this is like the concentration set gamma or pi. Then for each x, what should be the nature of this kind of piece? Let's say gamma x. Okay, and one may call it a splitting set. Okay, there's one question also related to this. It's kind of understanding a version of Brennan's theorem in this context. Okay, then of course the understanding that structure is also related to uniqueness of this martingale transport plan. Like in Brennan's case, by having Brennan's theorem, we also know that in certain general cases, the optimal transport plan is unique. It's kind of similar here. So we are aiming at a Brenner type theorem for martingale optimal transport. Question? Am I making sense here?
So in the traditional Brenier sense, you would perturb by measures with zero mass, and now we'd have some perturbation measures, which are like zero total mass and like signed measures, which also have zero mean. Is that kind of or zero cross-sectional mean?
Actually, I don't understand what you are talking about. Can you rephrase?
Like to obtain the optimality condition for the support of the optimal transport plan, you can perturb a transport plan by a signed measure such that it still obeys the constraint.
Yeah, you may possibly do that. Yeah, you may possibly do that, even though that's probably not what I'm going to do. Yeah.
Okay.
So what he's saying, okay, so if I understand this, the support of this, and let's say you have some optimal pi, then how do you get optimality condition? Maybe we find some kind of perturbation of this pi into another martingale transport plan, and then optimality means for all these perturbations, still the cost should be minimal at this. So then you get some kind of first order criticality condition for the optimal pi, and then you get some kind of structure. Yes, I think that's totally possible, and probably that is kind of hidden in things one can do. I mean, basically, the idea is just to use duality. Okay, you can solve the dual problem, and then after that you get some structure. Okay.
Yeah, that's a good idea. Thank you.
But probably what these people did was not to use duality, but probably something close to what you were suggesting. Okay, so so in 1D, they got this results. Okay, so from now on, let us focus on this cost. Oh, I didn't say. Let us focus on this distance cost. You don't want to consider distance squared, right? It's a squared cost is kind of trivial. So distance cost. So in Martingale transport problems, maybe this is the canonical cost. And then for that, in 1D, these people, like more than 10 years ago, got such a Brenier type result. Namely, let's say you have this convex order for the necessary condition to have any Martingale transport. And again, you have absolute continuity, okay? It's like in Brenier theorem, right? Then, and this is kind of technical condition that and they do not, so source measure and target measure do not overlap. So it's like you have mu here and then nu here. So they do not overlap, okay? Oh, so this is 2D picture, so I shouldn't draw it this way. So maybe let me change my picture. So in 1D, you have like mu here, and your nu is something like this. Okay, then what they found is the Martingale transport plan between this is like for each point, x here, you have only 2 target points. Okay, that's what they found. By the way, in this case, so we are focusing on the minimization case where we assume this. Then in this case, given x, this x has to move. It cannot stay there. So it will have exactly 2 target points corresponding to it. Okay. That's what they found. Of course, this is for almost every x. Okay, like in Brenier theorem, you cannot say for every x any like structure because of the measure zero phenomena. But for almost every x, you can tell the structure. And in this case, the structure is that the target points are only 2. But of course, if these target points, they have some kind of, they carry some kind of weight, like lambda 1, lambda 2 weight. Then that their weighted sum should be the same as x. And their weighted vector sum. So x should be the center point of these target points, right? When you have exactly 2. So in terms of the transport plan, each x you have like 2 points surrounding this y equals x, the diagonal. So the transport plan should be kind of union of 2 graphs. So that's kind of the phenomena here. So then with this structural theorem, you can prove that the optimal solution is unique. Okay, like in Brenier theorem. Once we have this structural theorem, Brenier theorem, then that helps us to show that the optimal solution is unique. So you can do the similar thing here. So maybe I should say, like in Brenier theorem. Okay, question.
Interesting to investigate how the optimal cost of the Martingale transport differ from the original problem. Is it an interesting topic to investigate, or you have no meaning?
Well, I mean, it depends. So the question was, would it would it be interesting? Okay, but in the whiteboard I see mass transportation. Would it be interesting to consider comparing the usual optimal transfer plan, the usual optimal transfer problem, and the Martin optimal transfer problem? Let's say even marginalized mu and nu. Let's say in the convex order. So then you can solve two problems, the usual optimal transfer problem and the Martin optimal transfer problem. And the question is there any question between them? I think this is extremely interesting question, at least to me, but I'm not sure whether people really investigate much in that direction. Yeah, maybe you want to check the literature.
Okay.
Yeah. Not only the cost, maybe, who knows, you want to consider the relation between the transfer plans. Okay. Regarding that, I have something to say regarding James' question. Compare the usual OT with martingale OT. And here there's an extremely interesting paper. Okay. I should say, this is extremely interesting paper. It's by Jules and Fatih and Jules. So F is before J, am I right?
F is before J in alphabetic order.
Yeah, I don't remember the title of the paper. They wrote something about so they made so-called martingale polar factorization. So yeah, so somehow given mu and nu, okay, they found some kind of a transportation. I mean, it's like a composition of transportation between mu and nu. One is to some measure, let's say mu bar, and then mu bar to nu. Okay, so here this first part is kind of Brownian transport. The other one is martingale transport. And important thing is that this Brownian transport satisfies Kaffarel's contraction. Have we talked about Kaffarel's contraction before in this course? Yeah. So yeah.
Means almost Gaussian transform of almost Gaussian variable.
So this is extremely interesting paper. So it somehow connect Brownian theorem. It's not in the sense you asked, but it somehow is also kind of fundamentally related to your question. Is that it somehow connected Brownian theorem, which is kind of part of this arrow, and then with martingale transport. Okay, so given two measures, you can find something in the middle, so that from this measure to that mu bar is okay. Of course, you can find a Brownian theorem. I mean the Brownian mapping, but the thing is that you have special Brownian mapping which satisfies a Kaffarel contraction, namely which is a Kaffarel contraction, namely this basically Hessian of phi is less than or equal to 1. So you have contraction, and then from there to nu is a martingale. So these two are in convex order. Okay.
Mu and bar mu.
Yeah, mu bar. Another measure.
Okay.
Yeah. So mu bar is a kind of result of some optimization coming from this given data mu and nu. Okay. So maybe let me move this comment. Okay, let me just keep it this way. Okay. Okay. Very good question. Anything else? Okay, now once you see this one-dimensional result, of course, I mean, we attempted to consider higher dimensional case. That's what we did. And then we found such a the following result. In general dimensions, Rn, we keep the same conditions as before, still the distant cost, and this absolute continuity of the source measure. Then for the optimal transfer plan, for example, you can prove that the concentration set, the support of the transport plane pi, I mean the slice of the source. So yeah, I already drew this. So let's say this is a pi, then each slice has its support. That's what gamma x is. Then the gamma x support, basically support of pi x is gamma x. I didn't say gamma x the support because you may it may not be the closure of the set where pi x is non-negative. But anyway, so gamma x is a set there. Gamma x of pi x is equal to 1. And gamma x of Rn minus sorry, I shouldn't, this is the reverse order. Pi x of gamma x is equal to 1, and pi x Rn minus gamma x equal to 0. So that is what I mean by this concentration set.
So what type of argument did you use to prove this?
Very good question. So duality. So, but before answering your question, let me just further say more results. Okay, this is kind of special, it's a corollary of what we did. But then what we did actually is toward this conjecture. It's kind of some progress toward this conjecture that under that conditions, if you consider, but by the way, do you understand the statement?
Yes.
Yeah, okay. So we want to understand structure of this set, gamma x, which I just called splitting set. So that's where basically this integration pi x is supported. So you just describe how the mass splits into the target points. Okay, so what should be the structure of the splitting? That's what this gamma x tells about. And then at least the splitting has to be n minus 1 dimensional. So for example, given x, okay, having this kind of pi x is not possible for optimal pi. It's not possible almost surely, almost everywhere, right? For optimal pi. I mean, the pi x has to surround this x to get x as kind of center point, but you cannot have this like a band of two-dimensional thing for this in 2D. If the dimension is R2, then the pi x has to be at most one-dimensional. Okay. So it has to be thin. But actually it's more than that. Yeah, so pi x can be like concentrate on this kind of circular thing in the 2D case. But the conjecture we formulate is this thing. You can actually there's concentration. I mean the definition of concentration set may not. Sorry, concentration set may not be unique because of this definition. It's kind of it ignores measure zero point in some way, right? So the concentration set has this structure. So given the set, whatever the set is, you take closure, and then you take the convex hull. So let's say if you have some set like this, you take a convex hull. That is exactly this filling this disk. Here in this example, if you have this set as your gamma x or gamma x, then such convex hull is just this one. If you have these 4 points, then the convex hull is kind of this simplex. Okay, then the point is gamma x, the splitting set should be the set of extreme points of such convex hull. So namely, it's not possible to have gamma x or gamma the closure gamma x bar having this and something in here. It's not possible because it has to be extreme points, meaning they should be along the boundary, but not just in the boundary, but they have to be some special points in the boundary. So for example, this kind of points in the boundary cannot be extreme points, but these points are okay. So extreme points are points on the boundary that has some curvature. Okay, so here you don't have curvature for these points. It's kind of flat. So then they are not extreme points. Here you have like very large curvature here. You just have this sharp point, and here they each points have curvature for the boundary. I mean the boundary have curvature at these points. Okay, and the same here. So extreme points. More precisely, the definition is this. So a point is an extreme points if you cannot realize that point with convex combination of other points in the set. Okay, so for example, this point in the middle is not an extreme point because you can realize this at you realize this point as a convex combination of these 2 points, right? Like here, this point can be realized as a convex combination of these 2 points. Okay, so these points are not extreme points or these interior points, but only like this point and these points are extreme points. So the point is that for optimal martingale transport, such splitting happens in an extreme way because its optimality kind of suggests that some special things should happen. Then this extreme property should be such a property. Okay, that's what this conjecture is about.
One Q and closed interval Q0 and Q1. Do you mean the straight line passing through Q0, Q1, and or Q2 and Q1, right?
Sorry? This one? Yeah, so
Closed interval of Q0 and Q1.
so here, let's say this is a whole set, right? Then this point is not an extreme point because you cannot realize this as convex combination of these 2 points. Many others. And this point is an extreme point because if you zoom in, then it's kind of curved. So this point cannot be realized by any other points because you cannot. Okay? Question? Okay. Okay, then toward this conjecture, we made some progress. You can do, okay, in 1D, that's what exactly this theorem tells. Okay, so this theorem is just the answer to that conjecture in 1D case, and in more general dimensions, one can do this in 2D, but also one can do this when this nu is not just convex order from with mu, but also it's more special that nu is realized by starting Brownian motion from this distribution mu, and then you stop this Brownian motion, and then you realize the target distribution. Okay, or if you don't like this, you can just new such an example new as like you apply some kind of diffusion partial differential equation like heat equation, or some motion than heat equation, then with this initial data mu, and then you see after some time the resulting distribution. If mu is such a distribution obtained by a diffusion, then with that mu and nu, you can do this structural. You can prove such a structural result that this splitting set has this extremal property.
So you're not requiring any disjointness of the supports of mu and nu then if you're gonna be relating
Yeah,
them
so
by
in minimization, so we said is disjointness. And because why disjointness? Because I mean, let's say if this is mu, and let's say, and this whole thing is nu, then of course for this overlapping part, the point x can just go to x. Okay, then and the remaining one goes to this I. So the transport can be like x and this y1, y2, y3.
Oh, okay, that makes
Target
sense.
points, target points, and then this point is not external point. Okay, so of course to have this theorem, you have to exclude this just identity mapping part. That's why you want to have some condition like this. Okay. Oh, by the way, so I assume that you understand this. This just mu, this mu, which nu is just the overlapping part. So it's like if mu is like this and nu is like this, then this is the overlapping part.
Right, and that's like impossible if we, under the second thing of your theorem, like if we just obtain nu from diffusion of mu, that would be impossible, right?
No, it's possible. I mean, you mean having this condition is impossible?
Right, yes, yes.
Oh, yeah. So you're right. So then that in that case you have to adjust, so this plus and union with x. Okay. And because in that case, whenever so in this case for the minimization problem, whenever you have overlap, then optimal transport for this overlapping part just x goes to x. Okay, so in that case you can kind of ignore that. Okay, so you can do that. And another thing is that for this more general case, you don't have. It's possible to move mu to this nu. Okay, or even this mu to just some lower dimensional lower dimensional supporting measure nu like this. So for more general condition, and this is possible. I will talk more about this thing, whatever it is. Okay, so in the okay. Question?
What's special about n equals to 2?
That's a good question. I don't have time to explain that. It's kind of yeah. So you want to read the paper? It is okay. So just to give you some hint, it is related to some lines, like aligned in this way. Okay. So then, so when you have these lines in 2D, if they don't want to overlap, then the angles they can make is limited if they keep some size. So if you have, let's say, each line segment have some size, let's say bigger than or equal to 1, okay? And they're all aligned, all kind of, you have family of such line segment, but the angles they can make is controlled in 2D because you cannot just break up, like you cannot just cross this way. But in 3D, it's not clear. It's not true even that your lines can kind of cross. I mean, it does not overlap, but can kind of cross this way. So you can make. You don't have control on the angle they can make. So this phenomena is related to why in 2D we can do this. But of course, why then line sigma, then all these things, it's a bit long story. So better to read the paper. I can explain in like, yeah, because I also have to cover the other parts. Yeah, okay? Yeah. Okay, so, and then here in this whole business, duality is just the hint, point, message. I didn't explain why, but duality has been a key in this progress. Okay? But remember, the duality was the key for almost anything in optimal transport, right? When you consider Brennier's theorem, at the heart, there is a duality. Okay, application of optimal transport to free boundary between water and ice. So somehow, this optimal transport can also be applied to this so-called Stefan problem, which is about the interface between two different phases, like water and ice. Like here, you have this melting ice, then you have this like a water region and ice region, and they make this boundary between them. So that's free boundary, and this boundary changes over time. So the free boundary is not just boundary in one space, it's just a boundary in the space-time. Okay? And so, but that's the usual scene you see in the nature, but sometimes you see this kind of phenomena. So this kind of phenomena which look very unstable and very like fractal-like. So it may happen, of course it happened, right? As in this photo. It is related to supercooled water freezing into ice. So there are situations where the water has temperature below the freezing temperature, but still unfrozen, still water, but the temperature can be very low. So this is very unstable situation. So if any stimulation happens to the water, then the water quickly freezes. But then this very quick change makes some instability and resulting this kind of very interesting shape. Okay. So this is like a supercooled water behavior. Okay, for this is the usual scene which you see, like it's kind of slowly water was slowly freezing or ice slowly melting to water. This is like stable behavior, but still understanding the free boundary even in this stable case is like a big problem in PDE theory. And in fact, Caffarelli in 1977 made one of the most important breakthroughs in that free boundary problems. And he later, I think almost, how long? 45 years later, he got Nobel Prize because of that. Oh, and many others. I mean, Caffarelli is really a big star in PD theories, right? But especially his work on free boundaries is the major citation in this Nobel Prize award. However, this unstable part is, I think, is widely open direction. Okay, but anyways, both problems are free boundary problems of education. So if you can write down the corresponding free boundary education. Okay, we are assuming the most simplified. We are considering the most simplified case. Okay, so then in the most simplified case, this stable problem looks like this, and this unstable problem looks like this, SPD. So on the left-hand side, this is nothing but the same equation coming from PD. Okay, I use this half here just because that's what probabilists use or considers. So this is our equation. Okay, this half is just a scale thingy, so it's not important, but it's a convention in probability. They consider this for some other reason. Okay, but anyways, so these are the PDs. Okay, first of all, let's start with the stable problem. So you have not just education, but with this additional term, sometimes called a source term, source or sometimes called sink. Okay, so this law governs kind of decay or increase of this distribution eta at each space-time point. So rho is a space-time function. Okay, and then, but the thing is, in the free boundary PDE, this function is first of all highly nonlinear and super singular. Okay. Okay, just singular. Okay, maybe super singular. So highly nonlinear because rho is a time derivative of this characteristic function of the zero set of eta. Okay, so this part gives the high nonlinearity. Eta to chi eta equals 0. This is highly nonlinear function, and this time derivative give. This is, I mean, this characteristic function looks like this, right? If you differentiate this, even in time, you get singular values. So this is a singular function. So that's why this problem is not so easy to handle and extremely difficult to handle. But Caffarelli fortunately made some big breakthroughs so that we can handle this. But of course, before Caffarelli, there are many other people who made important contributions to this, and before and after. But the supercus case, this unstable case, the PDs look almost the same. The only difference is this sign. So with just this different sign, the behavior is very different. It's kind of something common in PD theory. Once you change the sign, then things will change dramatically. Okay. So if you are doing PD, just be careful with for not making mistake in the sign. Sign is important. Okay. And this, I didn't explain this. Eta is the temperature. Okay. So water region is where the temperature is positive, ice region where temperature is 0. So in the stable case, eta is the temperature. But this unstable, I mean, the superconductor case, eta is not the temperature, it's minus temperature. So the temperature of the water is below 0, but temperature of the ice is 0. Okay? In the supercooled case. Anyways, that's not the whole, the main point of this slide. But anyways, the point is that these are like there are some interesting free boundary PDE. And then how can you approach this from the point of view of optimal transport? First, we need to consider transport. What should be the transport corresponding to these PDEs? And we know that this heat equation is related to Brownian motion. Okay, and Brownian motion carries mass. Given a point, Brownian motion carries that point mass to other points. Okay, so we try to view Brownian motion as a transport. Right, the Brownian motion carries the particle here and there, so it is a mass transport. Okay, and then this eta, it's just a result of the mass transport given by the Brownian motion. Okay, so if you just at each time t, this eta x is the distribution of the Brownian particles. Okay, at that time. So one can view Brownian motion can be understood as a transport plan between eta 0 and eta t, which is eta xt. Okay. So that's the point of view. But of course, then in that way, we can only realize that this heat equation, not the free boundary PDE. So then to get this free boundary PDE, the Brownian motion itself is not enough. Okay, and then this free boundary PDE can be possibly realized still with Brownian motion, but with so-called stopping time. So stopping time is like this. You have Brownian motion, then let's say this is time and space. Okay, so the heat equation or Brownian motion, Brownian motion is like at each time. Okay, so you this is a notation for PT. So okay, so you have Brownian motion at t at each. Okay, let me use. Okay, sorry. Oh my. Yeah. Okay, you have Brownian motion, and let's say this is like some time. Then this at each location Brownian motion move. So in the space time, so in space it just moves zigzag, but it's time, so it just this y coordinate increase, and then at time t you stop. Then you get this particle. So you start here, you have Brownian motion, then you get this particle. You start here, you have Brownian motion, and you stop there. So if this time at time 0, this underlying particle was like eta 0, then at t you get the corresponding distribution eta t. Okay, in this way. Make sense? But then this sink term I call it sync term. This term it kind of governs in this case disappearance of these Brownian particles. So Brownian particles in this new feature moves but stop there and then disappear there in the space-time. And another Brownian particle changes, keeps moving but stop there. Another Brownian particle moving and stop there. So the point is that each Brownian particles has some time to stop and disappear, but they do not share the same time. So in the usual Brownian motion, they have the same time to stop the Brownian motion. But in general, you may consider, each particle may have some freedom to choose when they die, right? When they disappear. So that is what this stopping means. Okay, and then with this stopping rule, which we call stopping time, one may possibly realize this more special PDE where you have this term, but then because of this expression, still, I mean, finding such stopping time, realizing this exact PDE is not easy. Yeah, I wouldn't say it should be easy. I think it's very difficult. But anyways, that's what one may try. Okay, I just explained what stopping time is. Okay. So the idea is to find an appropriate stopping time tau, realizing such PD. Then so the point is, so we view Brownian motion with stopping time as a transport plane. Okay, so that's the point of view. So finding some appropriate stopping time then makes this PD can be possibly translated into finding some optimal transport plan, while the transports are given by Brownian motion with stopping. So it is like the previous martingale condition. So in the martingale transport, you constrain the transport to be martingales. Okay. Now in this case, now we constrain the transport plans to be given by Brownian motion with certain stopping. Okay. So basically, you can understand this kind of so-called stopping time. So where these particles stop, this kind of stopping time as your transport plan. Am I making sense here? Okay, maybe questions.
Yeah, so first of all, when we add a source to the heat equation, how does that conserve the probability? Because my understanding is that we can apply this heat equation or the heat
Yeah.
kernel, like a Gaussian heat kernel, and it will conserve the mass of a probability
Yeah,
measure.
so this part will conserve, but this part will not conserve, right? So
Right,
so the thing is, if you combine eta and then this the rho integrate. So okay, so let's say eta at time t, eta t plus integral from 0 to t of this stopping, that is conserved. It's like this. It's very easy. You just consider this Brownian motion at each time. Let's say t. You have active Brownian motion still moving, and the Brownian motion already disappeared. Right? Fine. So then, because of this already disappeared Brownian motion, Brownian particles, the mass of these active particles is not the same as the initial mass. Am I right?
Yes.
But then if you add those already disappeared Brownian particles, then the total mass should be equal to the same as the initial mass.
Okay. Okay.
Okay? Yeah. Yeah, you're right. So just if you look at only eta, then eta does not conserve mass because of this symptom. But if you because eta together with integral rho, then you get the mass conservation. Okay. So in the end, I think you are asking this question because of this new. So here, I wrote this way. So this new is the distribution of the stopped. So this is stopped Brownian particles. Okay, so you start with your Brownian motion, many Brownian motions, and then you stop there, right? There and there, and then you look at where they are. So the distribution of these stopped particles is the target, and then if you can realize your given mu and nu with such stopping, then that is a transport plan between mu and nu with the constraint that the plan is a Brownian motion with stopping. Is this more clear?
Yes.
Okay. Is okay? Okay. Okay, then the idea is, okay, so given mu and nu, it is kind of similar to martingale transport problem. Do we have, even in the first place, do we have such transport plan given by Brownian motion with stopping? Okay, so you can consider such a problem, which is now famous problem called optimal corridor problem. So given mu and nu, can you find a stopping time, never mind optimal, a stopping time realizing such source and target measure? Okay, so that can be a question, right? And that's called the squirrel problem. And then one can solve this squirrel problem by actually optimizing this. So it is a bit complicated story, but so in here, of course, the existence was our question, right? Then why then even consider, how can we consider even like the optimal stopping one, even where we don't even know existence of such a stopping time, right? So so one way to consider this is like the following. So existence of such stopping time itself is not known, but you can consider maybe it's kind of technical term is can consider so-called randomized stopping time, which is similar to the control plan. So the stopping time itself is kind of like the finding a transport mapping, but one can kind of weaken the condition to have more like a generalized notion, and in this case called randomized stopping time. So there is randomized stopping time between mu and nu if mu and nu are in some order, which you call subharmonic order, i.e. You have the similar equation inequality as before, but for all C subharmonic instead of convex. Okay. So I think this is another famous theorem in probability. I always forget the name. I think this is I think is I guess it's Keller's theorem. Okay, so yeah, please check the literature. I'm always bad at this name. But anyways, So this infimum is taken over all randomized stopping time. So randomized stopping time is kind of generalized notion of stopping time. And then the point is that once you find the optimized such randomized stopping time, then optimized such randomized stopping is in fact the stopping time we were talking about, the Brownian motion stop at a time. But then it has some structure that you this optimized stopping times actually are heating times, namely, so this is Rn, that is time. Your Brownian motion moves, but you stop by hitting a certain set, which you call a barrier set. So the point is that optimal stopping time is the hitting time, the time it hits a certain barrier set. So that is a characterization of made by these people and others. Okay, so this is kind of similar. So this is, I would say, this is a version of Brownian's theorem. It characterizes how the transport happens, right? It says the transport happens by hitting a certain barrier in the context of Brownian stopping. Okay, and then to just say a little bit more, this barrier set is determined by the dual optimal solution, okay, of this problem. So you can view this one as primal problem, then there is a dual formulation, and then dual formulation is optimal solution. Then with that optimal solution, you can characterize such a barrier set. They are all in these papers. Okay, and one can consider this formulation to find a solution to this pre-boundary PDE by finding an appropriate Brownian stopping. So that's what we did with Inon Kim and also these other people. Okay, but there are some other stories, but I don't think I have more time for that. And anyways, this is still a very open direction, especially the supercode case, understanding this supercode phenomena. It's a very open direction, and then probably this Brownian stopping point of view may help. Okay, so I think that's what I can say. Okay, good. Okay, sorry, it's over time, so maybe I should stop recording.
I have a logistical question. Are you going to keep